In an informed culture, people are aware of the need for recycling. However, in large group gatherings, going out of one's way to recycle empty drink cans can be a chore for many. According to World Watch, about 190 to 210 billion aluminum cans are used globally per year. Americans use an estimated 100 billion cans per year, putting the USA far above the global average can use. In a country where so many cans are used, it's important to make the recycling of aluminum cans easy and quick. Especially in a college-age environment where many cans are emptied on a weekly basis, an in-home can crusher is a device that could be of high value to save time, space, and the earth. The design would need to be versatile, safe, and able to get the job done at a low price with minimal customer effort. When brainstorming and researching similar designs, the team came across a few patented ideas as well as some high-functioning prototypes on YouTube. One design we came across was made in the early 1980s as a single-arm lever-style can crusher. In this design, the can is crushed flat horizontally, where the circumference is crushed. The disadvantage, however, is that this design would require lifting up the handle and taking out the crushed can by hand. Also, there is no feeder mechanism, so cans would need to be loaded manually as well. This design, as well as a few others, led us to our first draft designs.
Design A is a crank slider mechanism featuring a feeder above point C to continuously load cans into the system. The slider at point C crushes cans to X length with a stroke of length S. There is no offset in this crank slider system, so the length of L1 is simply equal to half the stroke length. For every 180-degree turn of the crank with the handle at point B, the slider crushes one can. When one can is fully crushed and C is either fully extended or retracted, another can drops from the feeder to be crushed in the opposite direction. Design B also features a crank slider mechanism, however it is set up differently from Design A. The slider at point E is offset with the crank anchored at point A and has a limited theta range. The handle is at point C on this design and, as it is pushed down, the can is crushed towards the user using the slider. There is a feeder above the slider which drops a new can down every time E returns to its fully extended position. Design C differs from designs A and B principally because the crushing mechanism is a cam follower rather than a crank slider. There is a spring anchored between points A and B which, when compressed, crushes the can towards the wall using the slider at point D. This spring pushes the handle at B back into the starting position after the can is crushed. There is a feeder at D that drops in a new can every time it returns to its fully retracted position. The crush-it needs to be made of materials that are strong enough to crush a can. It must also only require human force to crush the cans. It needs to feed the cans into the machine smoothly and remove crushed cans in the same manner. The crush-it needs to be wall-mountable using tools that can be found at any hardware store.
The first prototype the team put together involved a base model of a can crusher with no feeder, as well as it needed to be hand-cranked. Moving forward, we needed to continue to simplify the prototype as well as figure out an easier and more reliable way to bring the design from the page to life.
Final design, as you can see, it's a wall-mounted system with a top-in gravity feed, and it's going to auto-gravity eject out the bottom into your trash can. So all you have to do is just pull the lever. As you can see, it holds up to 6 cans, and basically how that ejection system works is you have the 2 cans. One is currently in the chamber, the other one's sitting on top. As you can see, as you pull it, it'll crunch that can, and then the next can will come down. And as the can comes down, sometimes you have to finagle it. It's just because no 2 cans are the same, so it's hard to account for it. But as you can saw, the one can, after it was crushed, auto-ejected out of the bottom. And as the crush plate moves back, it tilts that can at an angle just enough, and then when the crush plate passes underneath of it, it straightens that can out to the point where it can perfectly fall right in front of the crush plate and then go through the cycle again.
To build our 2 prototypes, materials altogether came to around $80. However, this was on a small, non-commercialized production scale. If put on the market, close competitors are sold for around $30.
We definitely want to reduce cost, which would be easier now that we know exactly how much of each material we need. We could research cheaper materials in the future that would still be strong enough to withstand the force applied and would cost less. We also want to make the crush-it more aesthetically pleasing so that it will fit in with any home.